Let's start with a summary of oxidation reduction reactions. Redox reactions involve the transfer of electrons from one species to another. The substance that gains electrons is said to be reduced, while the substance that loses electrons is said to be oxidized. In the reaction that's shown, the copper metal atom loses an electron to become copper plus 1. Therefore, copper, in losing that electron, got oxidized. It loses the electron to the silver ion, which becomes then silver metal. The silver gains the electron, meaning that the silver plus ion got reduced. In order to keep track of which species loses electrons and which gains them, we assign oxidation numbers to individual atoms in the reaction. Here's a summary of how we might assign oxidation numbers. Elements in their elemental form always have an oxidation number of 0. For a compound, the sum of the oxidation numbers in a neutral compound is 0. For a monatomic ion, the oxidation number is always the same as its charge. For a polyatomic ion, the sum of the oxidation numbers is always the charge of the ion. Hydrogen has a -1 oxidation number when bonded to a metal and a +1 when bonded to a nonmetal. Fluorine always has an oxidation number of -1. The other halogens are usually -1, but in an oxyanion, so that's an anion that includes oxygen, they may have a positive oxidation number. Nonmetals usually have negative oxidation numbers, although in certain compounds or ions they're positive. And oxygen has an oxidation number of -2, except in the peroxide ion, which is H2O2 ion. In that case, the oxygen is -1. All right, so this table shows a summary of the two halves of what's happening. So the first half reaction is the oxidation. That's the losing of electrons. So losing electrons is oxidation, or we have the abbreviation LEO there. In that case, the oxidation state increases or becomes more positive. And as you can see here, the electrons are the product. We've lost an electron here. Reduction, the other half of the reaction, is the gaining of electrons. So gaining electrons is reduction, which is where we get this abbreviation GR. And the oxidation state decreases, or the number becomes more negative as electrons are gained. And electrons are a reactant. So this magnesium ion gains 2 electrons to become Mg solid. You can remember it through the mnemonic device of Leo the lion says grr. Another one, I'll just give you in case you've seen it, is oil, O-I-L, rig, which means oxidation is loss of electrons, reduction is gain. All right, so one thing to note is that redox reactions don't happen in isolation. You can't have an oxidation reaction without simultaneously having a reduction reaction. So any substance that gets oxidized is called a reducing agent or reducer, because the electrons lost in the oxidation will be gained by another species. Good reducing agents must easily lose their electrons. Neutral metals or substances with low ionization energies fit the bill, as shown by the examples. Any substance that gets reduced is called an oxidizing agent or oxidizer, because the electrons gained will be lost by another species. They must come from somewhere. Good oxidizing agents must gain electrons easily. Neutral or positive nonmetals or highly positive metals fit the bill here. So you can see some of those here. Reducing agents are oxidized, oxidizing agents are reduced. All right, let's go over how we balance redox reactions using the half reaction method. In a redox reaction, both the atoms and the electrons must be balanced. So let's look at this example. Let's start with the copper. So we start with copper 2+, and we can see just by following this blue arrow that it gains 2 electrons in order to become a neutrally charged metal here. Silver starts out as a solid and loses 1 electron to become a +1 ion. So even though there is one of each atom on each side, the equation is not balanced because the number of electrons lost does not equal the number of electrons gained. In this case, this can be changed by reacting more silver atoms, so more electrons are lost. So if we simply just add a second silver, now we lose 2 electrons, 1 for each of those silver atoms, to form 2 silver ions. And so now we've gained 2 electrons, and where did they go? Or where did they come from? They came from each of these silver atoms losing 2 electrons. As we've talked about in a previous presentation, chemical reactions are classified by what process is occurring by means of the reaction. Precipitation reactions involve the formation of a solid from mixing 2 aqueous solutions. There's a net ionic equation shown for the formation of cobalt-2 hydroxide. Acid-base reactions involve an exchange of hydronium ions or H+ ions, as shown in the neutralization reaction of ammonium with hydroxide. Redox reactions involve the exchange of electrons, as you can see in the example where magnesium loses 2 electrons, zinc gains those 2 electrons to form the 2 different products. There are a few reactions that do not neatly fit into one of these categories that we will deal with later. There's a special type of oxidation reduction reaction called a disproportionation reaction. In a disproportionation reaction, the same element becomes both oxidized and reduced. So let's look at this example here where we have these oxidation states. Chlorine is -1, okay? And because there are 2 of them, that means each of these mercuries must be +1. Now on the product side, we have mercury in its elemental form, so it has an oxidation state of 0. Chlorine again is -1. If there are 2 of them, then this mercury must be +2 to balance it out. So in this case, mercury is both oxidized, first going from +1 to +2, okay, so losing an electron, and reduced. It gains an electron and going from +1 to 0. So we call this a disproportionation reaction. Let's talk now about what we might see in a lab when performing a redox reaction inside of an electrochemical or voltaic cell. If we separate the 2 half reactions into separate beakers, we can capture the electric energy generated by the flow of electrons between the 2 half reactions. Remember that these reactions don't occur in isolation. If electrons are lost by one species, they are gained by the other. The energy released in a spontaneous reaction can be used to perform electrical work. Such a setup through which we can transfer electrons is called a voltaic, galvanic, or electrochemical cell. It is also called a battery. In the reaction we're going to discuss in the next several slides, we have zinc metal plus copper 2+, that means copper in the solution, producing the zinc 2+ plus copper metal. Okay? All right, so how do we set up this electrochemical cell? So we start out by putting the solids, the copper metal and the zinc metal, in 2 different beakers. The oxidation reaction that happens at the zinc results in excess electrons on the zinc electrode. So what's happening here, the oxidation is happening where zinc metal becomes zinc 2+, and then it loses those 2 electrons, okay? So the zinc has a relatively negative electric charge, repelling electrons or moving them through the circuit. The copper electrode has a relatively positive charge, attracting electrons through the circuit. The source of the electrons is called the anode, and oxidation is what occurs at the anode. And the sink of the electrons, or where they go to, is called the cathode. Reduction occurs at the cathode. The anode is always the electrode at which oxidation occurs. The cathode is always the electrode at which reduction occurs. So we can see that here. Electrons are flowing, and so reduction occurs here where the electrons are transferred to there. So the gain of electrons happens here, which is reduction. This can be remembered by using the mnemonic anox red cat, where anode is oxidation, reduction is cathode. Electrons are generated at the anode and flow through the external circuit to the cathode, as demonstrated by this arrow here. One last note about the electrochemical cell as it relates to this salt bridge that you can see in the middle. The flow of electrons from the anode to the cathode leads to an imbalance of charge between the beakers. That would stop the reaction and the flow of electrons if not corrected. The correction is made by the addition of a salt bridge. The salt supplies the needed anions and cations that flow to the beakers to rebalance the charge. The anions and cations in the reaction do not move through the bridge, just those of the salt. So, see how this says there's copper sulfate solution and zinc sulfate solution? So, it just, this is a solution of copper ions and a solution of zinc ions. And with the addition of extra electrons, you can get a bunch of extras there. So we have this salt bridge made of potassium nitrate that allows the positive potassium to flow this way to balance out the excess electrons, and the negatively charged nitrates to flow this way to balance out the loss of those electrons. Let's talk now about standard reduction potentials. Electrode potential is the tendency of an electrode to lose or gain electrons. In other words, it's its oxidation or reduction potential. By convention, the process is viewed as reduction and the values are reported as reduction potential. Standard reduction potentials, or E0 subscript RED for reduction, are calculated at standard conditions of 25 degrees Celsius, 1 atmosphere, and a concentration of 1 molar. These potentials lead to an electrochemical activity series. Standard reduction potential values provide a ranking system to determine which elements react more easily. Hydrogen is used as a reference point. The more negative the value, the less likely reduction will take place at that electrode, and the more likely oxidation will. These are the most reactive metals. The more positive the value, the more likely reduction will take place at that electrode, and the less likely oxidation will take place. These are the least reactive metals. Here's a chart that summarizes these reduction potentials. You can see hydrogen in blue right here in the middle, okay, as our reference point. As we go up, the values become more and more negative, okay, more and more negative. These are the most reactive of the metals, okay? So the top here, these are called strong reducing agents, okay? Strong reducing agents because they're most likely to become oxidized. They're most likely to lose their electrons and be the reducer. As we go this way, down the chart, the numbers get more positive. Okay, these are the most reactive. This is the most reactive of the non-metal here, fluorine. Okay, they have a very low tendency to lose electrons. Okay. They are weak reducing agents, which means they are very strongly oxidized. Okay, very strongly oxidized. Now, we can create a similar pattern with so these are all reversible reactions, right? So we can look at the reactants here, and essentially the reverse is true, okay? So towards the bottom here, at the bottom left, we would have a strong reducing agent, right? Or a strong oxidizing agent, sorry, or very easily reduced, right? Strong oxidizing agent means that that is being reduced. And then as we go up at the top left here, we have a low tendency to gain electrons. So that would be a weak oxidizing agent. All right, now that we have talked a little bit about standard reduction potentials, let's talk some more about oxidizing and reducing agents. So I just want to remind us of something. Oxidizing agents are reduced and reduction agents are oxidized. Remember that in a redox reaction, these two things happen oxidized simultaneously, right? Loss of electrons by one species in the reaction results in gain of electron by another. Okay, so I picked out a few of the reduction potentials from the chart linked on the previous slide. And I've just got them in order from highest reduction potential to lowest, being this negative 2.92. Okay, so as a reminder, the higher the reduction potential, more likely to be reduced. Okay, and the more negative, the more likely to be oxidized. Because remember, we're reporting these potentials in terms of reduction. So if it's greater than 0, that means that reduction is likely to happen, and if it's less than 0, then it's not. Okay? So if something is likely to be reduction, like we see in the top here, then this will be doing the oxidizing, right? Something that is an oxidizing agent gets reduced. So that's why we see this arrow here as we go up. We have increasing strength of oxidizing agent. So over here we have strong oxidizing agent. And then the reverse is true. On the other side, we see this arrow going down. The more likely something is to be oxidized, as it's oxidized, that makes it a strong reduction agent or reducing agent. Okay? So the strongest reducing agents, down here we see this one, have the most negative reduction potentials. They make better anodes. Why is that? Well, because oxidation occurs at the anode, right? Oxidation and anode both start with vowels to help you remember that, okay? Oxidation occurs at the anode. So strongest reducing agents are oxidized. That will be your anode. The strongest oxidizing agents, on the flip side, over here, have the most positive reduction potentials. They make better cathodes. Why? Because reduction occurs at the cathode. To help you remember that, reduction and cathode both start with consonants. Cell potentials. Cell potential is an intensive property. It does not depend on the amount of substance and is not affected by reaction coefficients. The electrochemical cell potential, E0 cell, can be calculated by the following equation, where E0 cell is equal to E0 times the reduction potential of the cathode minus the E0 reduction potential of the anode. So cathode minus the anode. The greater the difference between the two electrode potentials, the greater the voltage of the cell. For example, at the cathode, this reduction is taking place. This is the same example we've been seeing, where copper is being reduced, gaining these two electrons to become the copper solid. There's a standard reduction potential there equal to positive 0.34 volts. At the anode, oxidation is occurring, where zinc 2+ ions are gaining these two electrons to become zinc metal. That has a reduction potential equal to minus 0.76 volts. The E cell is just the difference between the cathode minus the anode. So 0.34 minus, and be careful of this negative sign here, negative 0.76 volts, which is positive 110 volts. The Gibbs free energy, remember that helps us predict spontaneity. So the Gibbs free energy, delta G0, for a redox reaction under standard conditions is inversely proportional to the cell potential. If the cell potential is positive, the reaction will occur spontaneously.